and he will give his talk on, I cannot see the title. So,
okay.
So generalized fractional Ostrowski and Grüss type inequalities involving several Banach algebra valued functions. So thank you, George.
Thank you, Eulalia. Okay, that's the title of the talk. I'm going to give a fractional interpretation of this type of inequalities, generalized, in fact, fractional interpretation. This is what will be based on left and right vectorial Taylor fractional formulae. So, to mention you, the famous Ostrowski inequality of 1938 is very simple but extremely important. F from A, B to reals continuous and differentiable with first derivative bounded. It has a sup finite. Then the absolute value of the average of the function minus f of x is smaller or equal than this number, 1/4 plus x minus a plus b square, a plus b half square over b minus a square times b minus a times the sup of the first derivative of f. This is true for any x. You see, there is x on the left-hand side and x on the right-hand side. On the right-hand side, you see constants, a, b, and you see also the norm of the derivative. On the left-hand side, you see integral against value of the function. The constant 1/4 is the best possible. So I'm going to generalize this inequality to very, very general for several functions to fractional level. And these Ostrowski types inequalities have great applications to integral approximations in numerical analysis. Another inequality I'm going to generalize related to Ostrowski is of Chebyshev. Very similar also to Grüss inequality. 1882. F of g absolutely continuous functions with f prime g prime L infinity. Then you see integral of product minus product of, rather you have averages, but basically it's integral of product minus product of integrals smaller or equal constant. Okay, so we assume that the above integrals exist. Okay, this has great applications in probability, in fact, in correlation, and has also its own merit to be investigated for the people who deal with inequalities. In my book 2016, this one here, Intelligent Comparison Analytic Inequalities, on chapter 8, I generalized these Ostrowski and Grüss Chebyshev type inequalities for several functions, not only one, several functions, to all positive directions. And over there, I use left and right Caputo fractional derivatives. And of course, there the functions are real valued. Okay. And in many other books of mine, I have dealt a lot with Ostrowski inequalities, and other people, of course, done research along these lines, especially my friend Dragomir in Australia, Romanian mathematician in Australia. He's one of the top inequality people, Sever Dragomir. Okay, so we are going to go very general. Okay, of course, at the end, I'll give applications. Okay, first, I need to mention you about the fractional calculus entities. These are in my book, my other book, Intelligent Computations, Abstract Fractional Calculus Inequalities and Applications, 2018. The other one was 2016. Okay. Let alpha positive, the ceiling of alpha is n. this notation is the ceiling of the number, is the smallest integer above the number, and let f Cn a be to x. X is a Banach space. X norm is a Banach space. Let g C1 of a be strictly increasing, such that the inverse is n times continuous differential on GAGB. We define the left generalized g fractional derivative x value to f of order alpha. This is Caputo type, but very general, giving variety of such derivatives for different g's. Okay, gamma is the gamma function. The last integral is of Bochner type, and one can see Bochner integrals in Mikuzinski's book, also Alibrandi's book. They are well known, you know. If A is not natural, we have that this derivative, according to these assumptions, is continuous. And we said if n is integer, the derivative to be this. Okay? The zero order derivative coincides with the function. Similarly, I defined, if G is the identity map, then is the usual x value Caputo fractional derivative. Anyway. Now I define the right-hand side fractional derivative. Apparently, I needed both in order to achieve my purpose. And this number x in the Ostrowski inequality so can be any such number in the interval a and b. I need to combine both left and right fractional derivatives. So here is the d alpha order b minus g f of x is the right generalized z fractional x value derivative of f of order alpha. The last is again, this last integral is of Bochner type. So similar properties with the left-hand side. So it's a generalization of the usual right-hand side Caputo fractional derivative. Okay, let's skip that. And then from this book of mine of 2018, I show you, I produce some very important Taylor formulae. I mean, Taylor formulas, to my opinion, are of the most important in mathematics. They are used a lot in various applications. If alpha positive, n is the ceiling of alpha f c n a b x, x Banach space, g c1, strictly increasing, g inverse cn, in ga gb. Then I have this fractional derivative, Taylor formula, engaging the left-hand side generalized fractional derivative. And with the change of variable, the remainder becomes like that. Okay? So we work a lot with the remainder in this case. And then I have the other one, the right-hand side Taylor's inequality. If G was identity, then collapses to the usual fractional Taylor formulae, okay? The one you've seen here and there in different books. And again, with change of variable, I have this kind of remainder. Okay. If alpha goes between 0 and 1, the sums, like this one here, disappears, of course. Okay. Now, there is some Banach algebra background. I take it from the famous book by Walter Rudin, Functional Analysis. Okay? So, for those not familiar with the Banach algebra, I need to say these things. A complex Banach algebras were invented in 1939 in ex-Soviet Union by Gelfand. A complex algebra is a vector space A over the complex field C, on which the multiplication is defined like this: x, y, z, x, y, z. So you can have these operations, you know, associative property, right and left, you know, scalar alpha can go anywhere in the multiplication. So you can have 11, 12, and 13 valid. A Banach, if A was a Banach space with a norm, then the submultiplicative property is the defining definition for Banach algebra. Okay? And also it contains a unit element E. So with norm 1. So if so, then A is called Banach algebra. If the multiplication commutes, then the Banach algebra is called commutative. Okay, one can prove easily that the unit is unique and can prove also that the multiplication is a continuous operation. Okay, I skip that. What I keep from here, very important property, is if you have, please look 17 and 18. If this integral is a Bochner integral, okay, so it's Banach space valued, here is Banach algebra valued, and X is a member of the Banach algebra that is a vector, a fixed vector, then can go in and out the integral from left and right. That's very important property. Used a lot in what you are going to see next. Okay. Now we go to the main results. When I say mixed fractional Ostrowski type inequality, means that this X you saw in the very original Ostrowski inequality can be anything in the interval AB. And mixed because I use both fractional derivatives to achieve that, right and left. We start with a uniform estimate. Let A norm be a Banach algebra. X0 is in AB random but fixed for the moment. Alpha positive and N the ceiling. Now I involve several functions. R functions. Cn from AB to A and G is C1 of AB, strictly increasing such that the inverse is Cn of G8 GB, and I have initial conditions. Of course, if alpha is greater than 1, I need initial conditions. If alpha was between 0 and 1, then no initial conditions are needed. As you saw in the basic Ostrowski inequality, we don't use any initial conditions because we involve there only the first derivative. But here we're working generally. Okay. My functional theta F1 FR X0 is the sum from I1 to R, integral AB, its I goes here, Fi and Fi X0. All right. And I have the product of the functions, all functions except the I1. Here and there. You see, I have integral from A to B. You have the product of all functions except I. Here I have the Fi x dx. And over here I have the integral of all functions except the I function. And over here, Fi x0. So it's a big, great generalization of the basic, very basic Ostrowski functional of the left-hand side of the basic Ostrowski inequality. So, and I runs from 1 to R because I involve R functions. So I give estimates first regarding the subnorm, like the basic Ostrowski inequality, and then I do L1 and I give also LP, okay? So this functional is gonna be upper bounded by this quantity here. again, on the left, you have integrals and f, functions f at x0, like in the basic Ostrowski inequality. In the right-hand side, you do have constants and derivatives, subnorms of derivatives. And this is what happens here. Okay, I mean, on the right-hand side, I have fractional derivatives, left and right. I have the x naught, and I have the integrals of these functions with j different than I. Okay, so and I runs from 1 to r. So it's a very general. At the end, I'm going to give applications, and this monster is going to look kind of nice. You will see at the end. Please be patient. Okay, I'll sketch the proof. Okay, I have the initial conditions, assumption by the first theorem of Taylor, left-hand side Taylor. I have this difference to be the remainder. And by the other one for the right-hand side, I have this difference with the other remainder for all x in x0b and all x in ax0. I multiply, I mean, these are the foundation of the proof. I mean, with this, I'm going to build up the proof. 21, 22, I'm going to build up the proof. So I multiply these two from right, from the right with some multiplication in Banach algebras. It's not like the one we know, the numerical multiplication is multiplication with restriction. So now I multiply from the right-hand side, rather, excuse me, left-hand side, both. Okay, both are multiplied by these products. And then I add these two relations as separate groups. And then I integrate these from A to x0 and x0 to b. Okay. And then, so here is, excuse me. So I integrate these from x0 to b, the first one, and the other one from A to x0. And then I add them up and have a useful inequality, identity first, a useful identity. This is the, by definition, the functional we want to estimate, and this is equal what you see here, these two rows of integrals and functions. This is number 29. And then I take the norm to both sides. I use some additivity of the norm. I use the norm that can go in. I mean, if you have Bochner integrability, it can go in the integral. And then by the multiplicative law of Banach algebras, can be distributed like that, also go inside, okay? And then I continue with my estimations and I have my results. Let me mention the L1 estimate. If alpha is greater or equal 1 under the same assumptions, over here I can have L1 norms, okay? So I can have generalized fractional inequalities and L1 norms. Okay, I skip the proof. Also LP. Let's say P and Q are conjugates, and alpha greater than 1 over Q. Then this functional is smaller or equal these quantities. These are L LQ quantities, okay, LQ quantities. So I have this situation here with LQ estimates for the generalized Ostrowski functional. Okay, I skip the proof. Now, how we are going to go to generalized fractional Grüss type inequalities over Banach algebra? Okay, we'll show a uniform estimate. Let me repeat the assumptions. A norm is Banach algebra. A is between 0 and 1, Fi C1 AB A, I1 to R, GC1 strictly increasing, G inverse C1 G8 GB, X0 in AB. All as usual, same assumptions as theorem 10. And theta F1 FR X0 as in 19, which is the generalized Ostrowski functional. We assume we call M F1 FR the maximum over I1 to R. These fractional inequalities uniform norms to be finite. And denote by delta F1 FR, delta F1 FR, the integral from A to B, theta F1 FR X dx. So here is the generalized Grüss functional. You see here, sum from I1 to R, B minus A, integral from A to B, this product of functions Fi dx. You see here, you have separation of the integral, into two integrals. See that? Integral Fix, integral the product. Okay? So we estimate that. We have that this generalized Grüss functional, the norm of it is smaller or equal than M F1 FR B minus A squared GBGA to the alpha gamma alpha plus 1 times the sum of norms of products. Okay? So I'm going to skip the proof and go to, I have also an LP related estimate. LP, same assumptions, only now you have P and Q conjugates, alpha greater than 1 over Q smaller or equal 1, and X0 in AB. So NF1 FR is this max of LQ norms of generalized fractional derivatives, finite, and GF1 FR is the product of norms of products of norms of Fj functions, J different than I in LQ norm. And then this Grüss functional is smaller or equal to RP NF1 FR GF1 FR P plus 1 P alpha minus 1 plus 1 to 1 over P gamma alpha B minus 1 over B plus 1 GB minus J alpha minus 1 over Q. Okay, let's see. Okay, guys. I mean, it's complicated theory. I'll skip the proofs, but I'm going to give applications so you hopefully you have an appreciation of what I do. Okay? Okay. Look. Assume now that A norm is a commutative Banach algebra. Then immediately the functional, the sum I had here becomes R times the integral of the product of all functions minus sum I1 to R, AB, Fi, dx, Fi, x0. So the first reduction, assuming commutativity. Now, if alpha is between 0 and 1, then the Grüss functional, again, kind of reduced. You have the integral of all functions, and here you have separation of integrals. All functions except one integral and the other on another integral, I1 to R. Okay, now you are hopefully you have more appreciation. Look, if R is 2, you involve only 2 functions. Then the Ostrowski generalized functional will be this one, number 55. Just take a moment, look at it. I stop here so you see it and understand it. You have the integral of the product of the 2 functions, and f1 x0 times the integral of the other one, the f2, minus f2 at x0 times the integral of the first one. Okay? And if the functions are only 2, the Chebyshev-Grüss functional becomes this. Like similar the one in Chebyshev inequality at the very beginning. Integral of the product minus product of the integrals of the 2 functions when alpha is between 0 and 1. Okay? So these 2 are nice, compact, and look good. Okay, so applications of my theory to these 2. Let's see what we have. The Ostrowski will be the norm of Ostrowski functional smaller equal 1 over gamma alpha plus 1, sum from 1 to 2. The norm of fractional derivative, the right hand side one, composition with G inverse, and subnorm over GAG x0, and times constant times the integral, plus the other one with the left hand side derivative, similar thing, the analogous one. This is by theorem 10. Now, regarding the Chebyshev-Grüss inequality, this delta of f1, f2 is smaller or equal f1, f2, p minus a square, very compact and nice estimate by theorem 30. Now let's give more applications to this for 2 functions. G of t, say, is e to the t, the exponential. Then the Ostrowski functional smaller equal 1 over gamma alpha plus 1, the sum, and here you have the Caputo right and left fractional derivatives for e to the t, composition log. Okay? Okay. So let me. This is the first paper I talk about. Talk the references. I'm not yet done. That's the first part of my talk, okay? I have also something else to say related. 1 second. Okay. The Alibrandis Border Great Book, Infinite Dimensional Analysis, 3rd edition. My books, Fractional Differentiation Inequalities, contains a lot of fractional Ostrowski inequalities. Advances in Fractional Inequalities, 2011, that was 2009, contains enough about Ostrowski, fractional Ostrowski. Then the 1 to 16 I show you, and then the 218 I show you intelligent commutations. The Chebyshev paper, 1882, inspired by Sever Dragomir, great work or inequalities on Banach algebras, Ostrowski and Grüss, but they are not fractional though. And then Mikuzinski, Bochner integral, 1978, Ostrowski famous paper, 1938, and Gr&uuml functional analysis. Okay, Function Analysis, 1991. 1 second, please. 1 second, please. I need to, what I need to do not to lose you. Stop share and, okay. Share screen. I need to close that and go to the other one. Okay. Okay, friends. All right. So now you will see again Ostrowski and Grüss generalized fractional inequalities. But now the norms are specialized. They are not general norms, are the p-gt norms in von Neumann Banach algebras. Before even start, I want to say something about the references, where it's based. One second.
Thank you.
I'm not yet done, madam.
No?
No,
Okay.
no, I'm not yet done. That's the second part of my talk.
Ah, okay, sorry.
No problem. Sorry, me. Okay. That's the second paper I want to present. It's very similar to the other one. It's related rather. Okay. It's based on the great book of Zagreb Gibbs semigroups, operator theory. And then Simon, trace ideals and applications. Is based also on Bellman, let's see, Bellman, 1980, okay? Some inequalities for positive definite matrices. Okay, now I'm gonna talk about my paper. I'm not gonna repeat the same things, but I'm gonna go to the point, what is new here. Sorry for that. Okay. As I said now, the inequalities I'm going to present, the norm is going to be specific. So on the left and right hand side of my inequalities, the norms will be of p-gt norms, but different, not the same one. That's the interesting thing here. Okay, H is a complex Hilbert space. Theta of H is the Banach algebra of all bounded linear operators on H. That means operators from H to H. EI is an orthogonal basis of H, and we say that A belongs to B of H, is of trace class if norm 1 sum I on I absolute value of A, that's not the numerical absolute value, is another one, operator absolute value, EI finite. Okay, that's when we say A is of trace class and is denoted by A norm 1. Okay, we call trace of the trace class operator for A, B, 1 of H is trace of A sum A, EI. That's the inner product. Okay, all right. Now, I'm going to skip things, go to the essentials. An operator A in Banach algebra on H is said to belong to the von Neumann Saturn class B, P, H, P between greater or equal 1 less than infinity, if the p-gt norm is finite. Here I have trace of absolute value A to the power P to 1 over P. Again, absolute value to the P is an operator notation and not a power. Okay, that's an important definition for what you are going to see next. And if 1 is less than P less than Q, we have B1H subset of BPH subset of BQ of H subset of BH. These are all from the book of Banach. The last one I just showed you. And the norms go different direction. A1 greater or equal AP, greater or AQ, greater or equal A. So this goes as these numbers, this goes reverse. Okay. Some important inequalities I'm going to use is 28. Norm P norm of A B smaller or equal P norm of A times norm of B for A B in BPH. So that's the multiplicative subadditivity property. These are Banach algebras. All the BPs are star ideals, they call them. Also, they are Banach algebras. And the most important property is this one at the very bottom here. A times B is composition, it's not multiplication, it's composition. A composition B of norm 1 smaller or equal P norm of A times P Q norm of B when A is in BP and B is in BQ. Okay, all started by Bellman, the one I saw you, and then the other authors wrote interesting things, and then we are using this in the inequalities. Okay, what you are going to see now is the first theorem is the following. Let the star ideal B2 of H. B2 of H norm 2 is a Banach algebra. The rest of the assumptions are similar to those you saw in the first part of the talk. A positive N ceiling of alpha, AI, CNA, B2. I have a specific Banach algebra, B2. G C1, AB strictly increasing, a G inverse CN, G8, GB, and I have the initial conditions. Now the functions of phi, they are named AI, from CN, from AB to B2A. And the functional you saw in the first part of the paper, instead of I have the AIs now, is the generalized Ostrowski functional. And then I'll give without proof the following results. Starting with the LP result, let gamma delta greater than 1, 1 over gamma, 1 over delta 1, alpha greater than over delta. Then I have the norm 1 of the Ostrowski functional, smaller equal numbers times, look here, is the 2, everywhere you see the 2 norm. Okay, what is the interesting here is that the norms, they follow a decreasing order. But here, with this very last property of product AB1 smaller equal norm P times norm Q, this property I mentioned earlier, becomes the other way. Here you have 1, over here you have 2, increasing order, 1 less than 2. Okay? So it's a game with the norms, different norms, Saturn norms on von Neumann Banach algebras. If alpha is greater or equal to 1, then I have the corresponding L1. Okay, corresponding L1. And I can have also the uniform estimate. Again, on the left I have norm 1, on the right I have norms 2. Okay, I'm going to skip the proof. I'm going to give also talk about another similar result here, playing with the norms. Okay, I have here P and Q conjugates, and let the star ideals be P, B, Q. These are Banach algebras. Now I involve only 2. I cannot involve more than 2 functions. A1 from CN AB to BP, A2 from CN AB to BQ. And I have the initial conditions. I have the functional, which is quite lengthy now. And I have the estimates. the LP estimate. Here I have norm 1. Over here I have norm P, Q, P, Q, and then QP, QP. So it depends what I involve. A1 is involved here, A2 there. A2 is kind of technical, okay? And when alpha is greater than or equal to 1, I have the 1 here, the PQ there, etc. is L1 estimate on the outside norm. On the outside norm is L1 estimate. And of course, the uniform estimate, okay? So let's see for applications at the very end, so you have an appreciation of what's going on here. Applications. If G of t is t, the identity map, then the inequality becomes more compact, nicer. You have 1 here, 2 there, the norms, okay? The 3 estimates, the LP, the L1, and the L infinity, okay? And then another example with the 2 functions and PQ conjugates. I take a G of t, the exponential now. And I have here involved the exponential and the logarithmic, of course, different kind of estimates. And if alpha greater than 1, I have the L1 estimate, okay? And all possibilities. And at the very end, when G of t is a log of t, for t in AB, which is a subset of positive real numbers, I can have accordingly estimates. All P here, the 3 type of estimates, L1 and uniform. Okay, I can have also Grüss type. Let's take G of t, t. Then I have the Grüss functional, norm 1. Smaller, you have norm 2 here, okay? So 1 and 2 here is in increasing order. Over there, the properties of certain norms is in decreasing order. Anyway, I can have this interesting estimates. Okay, and let me go to the references. I don't want to hold you more. Dali Brandy's book, Infinite Dimensional Analysis, and the Bellman, Bellman paper started this certain norms theory, 1980. And the very important papers, Chang, Coop, relate to that, motivated by Dragomir papers on certain norm inequalities of Ostrowski and Grüss type. And then I have, of course, as I said, the Simon book, Trace Ideals and Their Applications, 1979, and Zagrebov Gibbs, Semi-Group Operator Theory. Okay, I'm done. Thank you for coming and attending my talk.
Thank you,
If there are
George.
any questions, I'll
Any
be happy to answer.
questions?
So again, this is an effort to try to apply fractional calculus in various areas of mathematics.
Sure. No, it's very interesting to see all these applications, indeed.
Yeah, trying to popularize fractions.
Yeah, definitely.
Because we deserve that, you know.
Are you going to Are you going to be in Cambridge at some point?
Sorry, I don't. Okay, I have some health problems. And I'm in protected
I see.
mode,
So you cannot travel.
Yeah, especially with COVID.